let's take a look at our last topic with number theory, least common multiple. As you can kind of tell in the name, instead of compared to greatest common divisor, we're now looking for the smallest, the least number that is a common multiple between two or more numbers. Okay, so our first method, intersection of sets, which by the way has the same name as the greatest common divisor, intersection of sets, we will list out multiples and look for that time when the least, the smallest number, where they both are the same. So let's take a look at an example. What is the least common multiple of 6 and 14? Well, what we can do is list out the multiples. I'm going to use a capital M to denote multiples of 6. Okay, we can start listing those out, and also list out the multiples of 14. I like to kind of list them out at the same time because we're not really sure how far to go with either list. I mean, the multiples of 6, 12, 18, and so on, they go forever. Okay, so we don't, where do we stop? So I might list out a few of the larger number first. I go, okay, well, 14. What's the next multiple? Well, 14 and 14 is 28. And then maybe I'm stuck. So maybe I grab a calculator. I go, well, 28 plus 14 more, that's 42. Now, for those of you that know your 6 times tables, you're like, whoa, wait. Others of you that may not have that chanted off quite as easily might not recognize that. But I'm going to stop there because I know that that feels like my answer. If I go back to the multiples of 6 for a second and list those out, 6, 12, 18, 24, 30, 36, 42. Notice that this number 42 appears on both the list. That is my least common multiple. It is the same number that appears in both lists, but the first occurrence of it. So we could continue the list and we would find that they would match again, but I want to stop now because I want the least number. So what I mean by that is, like, if you continue this list out, eventually you would get 84. And eventually here you would also get 84. In other words, they would match again. So that's a common multiple, but is not the least common multiple because that's the first time that they match. Okay, so if the numbers are relatively small, you might be able to do something like that. Let's take a look, though, at the prime factorization method and compare. Right? Prime factorization, well, it's just kind of what it sounds like. You have to look at the prime factors. So if you want the LCM of 6 and 14, you first list the prime factors of each. 6 is made up of 2 times 3, and 14 is made up of 2 times 7. And what you're going to do differently here is kind of build a number that has these factors in it. You can start with either number. I just will start with the top. I'm going to start with 6. 6 is made up of 2 times 3. So even if I don't know what my answer is, I know it must have a 2 times 3 in it because 2 times 3 is 6. Then I go to the next number on the list. It's made up of 2 times 7. Notice I'm already good. I already have a 2 there. So I don't need another 2. I just need a 7 to be able to build that. So I'm going to add in 7 to the list times 7. And then 2 times 3 times 7 happens to be 42. Same answer. So let's pause here for a second to see why this works. Notice that 2 times 3 is really 6, right? But 2 times 7 is really 14. So 2 times 3 times 7 has both a 6 and a 14 as a multiple, or should I say as a divisor. Okay, now this, you can see they may equally work well for smaller numbers. When you get to rather large numbers, though, you're going to want to use the prime factorization. Let's take a look at one more example. If I want to do the least common multiple of something large, let me come up with some rather large numbers here. Let's go back to that number I used in the previous video, 504. Okay, all right, let's do that with 1,260. If I were to list out the multiples of these numbers, I would be troubled right away. I'm like, okay, 504, what's that twice? 1,008, and then 1,512. It gets really tricky to do. And the multiples of 1,260 are even worse. So I think the prime factorization method is superior when the numbers get larger. So what you can do, you want to see this one more time, is first figure out what the prime factors of each are. So let's take a look. 504, well, what divides into that? I think it's divisible by 8, and it is. It's 8 times 63. All right. And then 8 is 4 times 2. 2 is prime, and 4 is 2 times 2, and those are both primes. 63 is 9 times 7. That's prime. And then 9 is 3 times 3. So 504 is made up of, well, lots of things. It's 2, 2, 2, 3, 3, 7. All right, the second number, 1,260. It ends in a 0, so I know it's 126 times 10. And then 10 is 2 times 5. 126 is an even number, so I'm going to divide it by 2. It's 2 times 63. All right, 2 is prime, and then 63 is 9 times 7. 7 is prime, and then 9 is 3 times 3. So it has prime factors 2. You can see I have another 2 in there. I have 2 3s, I have a 5, and I have a 7. Okay, now this looks a little overwhelming, but it actually should tell us the answer. So you might remember when I did it above, I said choose either number, it doesn't matter. I'll just choose the first number. I'm going to choose the 504. If my answer is going to have 504 as a multiple, it has to have all of those factors in there. So I'm just going to put all of those in there. 2, 2, 2, 3, 3, 7. Then when I go to the second number over here, I just look and see what is already there that I have, and what do I need to add in that I don't have there yet. Okay, do I have 2 2s already there? Yes, I do. So I'm okay. I don't no need to add those in. Right. So I'm gonna not worry about it. Do I have 2 3s? Yes, I do. Okay, don't have to add those in. Do I have a 5? No. So I must now add a 5. Now I got that satisfied. Right? Do I already have a 7? Yes, I do. So I don't need a 7. And that is my final answer. And the reason that it works is because you can see the first part of this number is made up of all the factors of 504. But if you include all the factors here at the back end, that's 1,260. So that is my final answer. If I multiply all those together using a calculator, I get 2,520. All right, 2,520 is the first time that those would match. Those are both methods.